this module, we will discuss various types of coherent receivers that are used in optical communications. In the previous module, we have discussed direct detection receiver as well as the self delay line interferometer detectors. Those detectors did not actually utilize a local phase reference. This local phase reference is given for coherent receivers by a form of a local oscillator. So, just as you have a transmit or a signal laser diode, you will have to have a laser diode at the receiver as well in order to generate the optical signal, which will be used as the reference signal to compare against the incoming signal. If you recall what is the basic coherent receiver system, you must have studied a super heterodyne receiver or a heterodyne receiver. The incoming signal, call this as some S of t, will be multiplied by a local oscillator, call this as some LO of t, okay, and then the resulting signal is processed further. If the incoming signal frequency is different from the local oscillator frequency, then you end up with what is called as a intermediate frequency. Your spectrum will be centered at the intermediate frequency, otherwise the spectrum will be centered at zero intermediate frequency. Zero intermediate frequency is nothing but DC, right. So, the principle of operation of this one would be that if I assume, for example, S of t to be sinusoidal signal, so let us say which is phase modulated. So, I have AS cos omega st, which is where omega s is the incoming signal frequency, the sinusoidal signal frequency. Its phase has been modulated, so its phase is theta s of t. And if I assume that the local oscillator signal has an amplitude of ALO, okay, and it also has a certain local oscillator frequency omega LO plus some usually constant phase offset, which is theta LO. So, if we assume that these are the two, then you can multiply them and then utilize the formula for cos A cos B, which will be something like half of cos A plus B plus half of cos A minus B. So, if you use this formula, because these two are cosine signals, I can multiply them. I will not show you the details, but this is a very simple fact that you can find from applying the trigonometric formula. What you end up, so if I call this signal as say R of t, what you end up after the mixer, this is a mixer or a multiplier, is this signal. So, you have AS ALO by 2, which is a common factor that I can take it out, and then you have two components, omega s plus omega LO t plus theta s of t plus theta LO. Okay. So, this particular cosine signal that you have here, a phase modulated cosine signal, is centered at a frequency omega s plus omega LO, which both of them are typically close to each other and they are very large. So, omega s could be, for example, 2.4 gigahertz and omega LO will be very close to that. It would be anywhere between say 1900 megahertz to 2800 megahertz. Okay. This is just an example frequency that I am considering. In optical signals, these frequencies are much different, but if you take omega s and omega LO both to be large as well as omega LO is approximately omega s, this signal, the one that we have written here, cos of omega s plus omega LO t, will be oscillating with a very large frequency. It is actually centered at a very high frequency, much higher compared to the intermediate frequency. Where is the intermediate frequency coming in? Well, this is the cos A plus B term. So, what we have is the plus term here. You will also have cos A minus B term, correct. So, for the cos A minus B term, what do you get? Cos of omega s minus omega LO t plus theta s of t minus theta LO. As I said, theta LO is just a constant or more or less a constant for many applications. So, you can safely ignore that, but what is interesting is that you get one spectrum which is centered at the difference frequency, which is omega s minus omega LO. We say that this is homodyne or 0 IF in when omega s is equal to omega LO. So, if you were to tune the local oscillator frequency to be equal to the incoming signal frequency, this omega s minus omega LO of t will be equal to 0, right. So, that the spectrum will be centered at omega IF, which is equal to 0. In other words, this would be centered at DC for homodyne or 0 IF transceivers. On the other hand, if omega LO is not equal to omega s, then we call this as heterodyne receiver. So, in this particular case, omega s is not equal to omega LO and the intermediate frequency is centered not at 0, but at some other frequency. Okay. Now, one can eliminate this omega s plus omega LO term, right. I can eliminate this term by filtering it out. So, if I put in a filter which will only pass the signal which is centered at omega IF and rejects this other signal omega s plus omega LO signal, then this term can be eliminated. Okay. So, I have a filter, essentially a filter centered at omega IF, so that only the signal around that will be transmitted, and this high frequency signal which is oscillating at omega s plus omega LO can be eliminated. So, a coherent receiver, or sometimes called as a synchronous receiver, is basically consists of a multiplier in order to generate a signal at omega IF followed by a filter. Okay. This filter will be centered at omega IF. It is essentially a band pass filter if omega IF is not 0, or it would be a low pass filter if omega IF is equal to 0. Now, this is a general receiver that you are probably familiar with. Now, how do we implement this optically? Do I have an optical multiplier? Turns out that I do not have an optical multiplier. So, what do I do? Well, look at this scheme. Okay. You have an incoming signal. Because this is optical, we will switch to the electric field notation for this. So, I have Es of t, which is the incoming signal which is modulated at the transmitter. If I put in a coupler, a device which we discussed in the previous module, if I put in a coupler, and to this coupler I send in one more signal which is the local oscillator. Okay. So, I can write down the local oscillator as ELO of t. It is also a local oscillator. This signal will be characterized by its frequency omega s and its phase theta s of t. Okay. It will also be characterized by its power, which is Ps. Finally, it will be characterized also by its amplitude changes A of t. Obviously, this C of t, the complex envelope of the modulation, is given by A of t into e power j theta s of t, correct. So, this A of t is the amplitude modulation part and theta s of t is the phase modulation part. For a BPSK signal, A of t is constant, is equal to 1 for example, whereas theta s of t is 0 and pi. For a QPSK signal, A of t is different, or you can think of A of t as constant, but theta s of t being pi by 4, 3 pi by 4, 7 pi by 4 and 5 pi by 4. For a general QAM signal, both A of t as well as theta s of t will change. Okay. So, giving rise to a general QAM signal, and the objective of the receiver, the optical receiver, would be to extract both A of t as well as theta s of t. So, this incoming signal is characterized by all these parameters. The local oscillator is characterized by its local oscillator power, its frequency offset theta LO. This theta LO is also varying, but since this is an oscillator which is under our control, we can keep these oscillations to minimum. In other words, we can spend a lot of money to purchase good quality local oscillators if cost is not an issue for us, and for long haul communication systems, it is especially important to have pure local oscillators whose phase noise is very small. Now, this device is the coupler. We have already seen how to relate these outputs of the coupler. We had written down a general coupler configuration with E1, E2, E3 and E4, and we said that E3 and E4 are characterized by certain matrix. For a 50-50 coupler, this is 1 by root 2 1j j1 times the incoming signal, right, or the input signals E1 and E2, right. So, this would give me the output relation to the input relation. It is also possible to actually fabricate a coupler whose relationship is slightly different. This becomes 1 and this becomes minus 1. That is to say, I can fabricate a coupler by adjusting the phase or the length of the coupling element, something that we will study later, which will then give me which will then give me a coupling matrix which is 1, 1, minus 1 and 1. This 1 by root 2 indicates that the amplitudes are getting split into 1 by root 2, so that the powers are getting split into half. Okay. So, applying this coupler matrix to the equation and then for the moment neglecting this part, what do I get at this output port? What do I get at this output port? I get Es of t plus ELO of t divided by root 2. This is the electric field or the light beam that I am going to get at the output of the coupler. Please remember, this Es of t is the incoming light which is modulated coming from the fiber, and then it has been amplified, filtered and all that. Now that is being mixed or coupled with the local oscillator light beam. This is also light, this is also light. This device basically mixes two optical fields or optical signals to generate Es of t plus ELO of t by root 2. Okay. Next what we do is we put in a photodetector. We put in a photodetector and then look what happens at the output of the photodetector. If I call the output of the photodetector as the photocurrent IPH of t, pH stands for the photocurrent in our notation. So, IPH of t is given by 1/2 because the photocurrent is proportional to the intensity of the incoming signal, right. So, intensity is electric field square, mod electric field square, and there is also a proportionality constant which is called as responsivity of the photodiode. This responsivity is usually given by or given in terms of ampere per watt. Okay. So, if I put in 1 watt of optical power, I get 1 ampere of photocurrent. Okay. So, this value is given typically in ampere per watt. So, if I now do Es of t plus ELO of t mod square, what I get is Es of t square plus this r into 1/2 is a constant. So, I am going to remove that one outside. I get ELO of t magnitude square plus 2 times real part of Es of t ELO complex conjugate of t. If you are surprised by this, please remember that we have been following the phasor notation for the optical fields, right. Our incoming signal Es of t is actually given as A of t e to the power j omega s t plus theta s of t. There is also square root of Ps. This is the incoming signal. The local oscillator signal will also be given in the phasor notation as square root of PLO e to the power, it is not modulated. So, it is simply e to the power j omega LO of t plus theta LO. Okay. So, if you substitute these two expressions and then simplify, the photocurrent will consist of 3 terms. The first term is R by 2 PR, okay, where PR is equal to PS A of t magnitude square. Okay. PS is the incoming signal amplitude. So, PS A of t magnitude square. This e to the power j omega s t plus theta s of t will go away because of the modulus operation. The second term is R by 2 PLO. PLO is the local oscillator power. Okay. And finally, the third term which you are interested will be R by 2 square root of PS PLO. There is A of t, I have assumed A of t to be real, therefore, I pulled out A of t outside and then I get real part of this. So, if you take the complex conjugate of the local oscillator field, you will get e to the power minus j omega LO of t LOT plus theta LO. So, if you put in that into this expression, what you see is cos of omega s minus omega LO t plus theta s of t minus theta LO. As I said, theta LO is just a constant for you, okay, for us in this particular scenario. So, you can safely eliminate this theta LO. Well, safely is probably a strong word, but for now we can eliminate this theta LO. Okay. Now, do you observe that whatever the third term that you have obtained, if you leave out the proportionality constants, is exactly the same thing as you have obtained from the typical heterodyne receiver that we have considered earlier, correct. So, in the earlier case where we considered the heterodyne receiver, you had the output which was cos of omega s minus omega LO t plus theta s of t minus theta LO, where theta LO was the phase of the local oscillator, which if you remove it will then become exactly equal to the signal that you have obtained in this case. So, what you have done is to take two optical signals and then realize the multiplication operation without actually having a multiplier. We do not have a multiplier in the optical domain, but you have realized a multiplier in the optical domain by this operation. Okay. Couple of points: PLO is typically much larger than PS, therefore, the first term can be neglected in comparison to the second term. So, neglect that in comparison to the second term. The second term is essentially DC, okay, because you are not modulating the local oscillator. This is a DC signal for us. So, it simply means that this time varying information is riding on this DC signal, right. So, you have, if you look at it as a function of time, there is a DC signal which corresponds to R by 2 PLO, and then there is a time varying signal, okay, which corresponds to R by 2 square root PS PLO and whatever that other factor A of t cos omega s minus omega L O something. Again, this would be heterodyne when omega s is not equal to omega L O. This is called as homodyne when omega s is equal to omega L O. Okay. So, when omega s is equal to omega L O, the third term simply becomes R by 2 square root PS PLO A of t cos of theta st. So, you have managed to obtain the photocurrent, and if I am neglecting the DC part, of course, I have neglected the DC part here, the time varying component is given by a new value of effective responsivity. You know, the simple photodetector has a responsivity of R, this one has a photodetector responsivity, an effective photoresponsivity of R by 2 square root of PS PLO, and PS PLO will be very large, typically very large chosen, so that the effective R is much larger than the simple R that you obtain. In other words, because R effective is larger than R, this is much more sensitive, okay, compared to direct detection receiver. In fact, this sensitivity was the main factor which people were trying to capture by going into the coherent receiver designs in the early 90s, but the problem is that you need to have a good phase relationship, right. So, we have to establish a definite phase relationship with the incoming signal. While the local oscillator is, while the incoming signal is cos of theta s of t, right, the local oscillator signal should be tuned exactly to omega s if I am implementing homodyne. Moreover, it must also have a definite phase relationship. While this is cos, that incoming signal is also cos. If the incoming signal is cos, I cannot have a local oscillator which is sine, then they will not mix pretty well. So, this was actually realized in two ways. If you talk about heterodyne receivers, you can then put a electrical PLL, a PLL being a phase locked loop. What do I do? This is the photocurrent after removing the DC part, this is the AC part of the photocurrent. Okay. So, this AC part of the photocurrent, if you look, it will have this frequency offset omega s minus omega L O, the difference is the frequency offset, which you can somehow estimate and correct, and then in addition to theta s of t, there will also be this minus theta L O, right. You can control this theta L O such that it will track this signal theta s of t. While theta s of t is the modulating signal, in reality there is also another phase component that sits in the incoming signal. This is called as the phase noise of the transmit lasers. Okay. In addition to this, there would be other types of phase noises, not just the laser diode phase noise, the fiber also introduces certain amount of phase noise. All these things will degrade the performance of the coherent receiver system unless you are able to track it. To track that, you take this signal, now this is in the electrical domain, what you do is you simply take this IPH of t, right, multiply this one by a microwave or an RF local oscillator whose frequency is omega IF and which has a certain phase theta IF, okay, and then you get this signal, you adjust based on the output this local oscillator frequency as well as the phase. Okay. So, this PLL that you are implementing is in the electrical domain, which is much simpler than implementing a PLL in the optical domain. Okay. However, the problem is heterodyne is not as sensitive as homodyne, So, you want to be able to use the homodyne coherent receiver, but if you want to use homodyne coherent receiver, you have to build a optical phase locked loop, right. So, you want to build an optical phase locked loop, or you can exploit very nice DSP algorithms in order to extract the phase, okay, or estimate the phase. This is the technology that is currently being used. So, we use high speed DSPs in order to estimate the phase of the incoming signal in order to perform carrier recovery as well as for synchronizing our local oscillator with the incoming signal, okay. Something that we will talk about it later in the course. Okay. We have talked about the coherent receiver homodyne. One thing you might have noticed is that this photocurrent that we have obtained. So, if you look at this photocurrent is only extracting A of t cosine of theta st. What happened to sine theta st? Well, I need to extract that also, right. So, I can extract that sine theta s of t by altering this coherent receiver in a slightly different way. So, I take the incoming signal as it is, which is Es of t, and then put it through the coupler, but instead of sending this signal from the local oscillator directly coupling it to the directly to the coupler, what I do is I send it through a phase modulator, okay. I send this through a phase modulator and set the phase modulator such that it provides 90° phase, which means that instead of ELO of t going into the coupler, what you get is JELO of t. So, if ELO is cos signal here, after phase modulation this becomes sine. So, now you compare your incoming signal with sine and then you will be able to extract it. Like if you look at the output, again for the moment neglecting this second arm, if you look at the output you will find the signal component, so Es of t mod square after putting a photodetector, of course. So, if you put a photodetector you get 3 terms, Es of t mod square, you get ELO of t, rather you get JELO of t mod square, but because phase has no value for the power, this is as good as just getting PLO here and as good as getting PR here. I am removing this R by 2 factors, you can fill in those later, and then finally what you get is real part of e to the power j omega I of t plus theta s of t minus pi by 2. Why do I have to put a minus pi by 2? Remember, you want to find out ELO complex conjugate of t, right. So, I need to put in ELO complex conjugate. This j can be written as e to the power j pi by 2. So, when I take the complex conjugate, this becomes e to the power minus j pi by 2. So, because of this, this minus pi by 2 goes into this one, and what is cos of something minus pi by 2? It is sine of that quantity, right. So, this real part becomes sine, and assuming omega if is equal to 0 for the homodyne case, I get sine theta s of t, A of t is as it is appearing. So, I have now obtained by using 2 different couplers and 4 different, or at least in this case I have used 2 different photodiodes, okay. What I have obtained is some DC quantity plus A of t cos theta s of t, some DC plus A of t sin theta s of t, okay. These are 2 electrical signals, these are the photocurrents, one is the in phase component, the other is the quadrature component, okay. So, I have obtained in phase as well as quadrature component. By using some electrical means, I can add them after multiplying the quadrature component by j, okay, and then adding them in order to obtain both in phase as well as quadrature component. So, I will actually be able to extract this C of t, which is the complex envelope that we had used, the modulation signal complex amplitude. You will be able to extract this C of t. You might be asking one additional question, well, how about this DC term? Is there anything that I can do to eliminate the DC term? Yes, there is. In fact, if you look at this term which we have neglected here, right, this other port which we have neglected, this one which we have neglected here, rather than neglecting it, let us put it to some use. See what do you get at the output, okay. So, what you get at the output after photodetector will be JELO of t mod square, and instead of having real part of something over here with a plus sign, you get a minus sign. Why do I get a minus sign? Go back to the matrix of the coupler. This term is ES plus ELO, whereas this term is ES minus ELO. So, I get minus, I will just write down only that part. So, I get minus real part of e to the power j something something very similar. Now, what I do is I subtract them by putting up a electrical subtractor. These are two photocurrents. I can put maybe one op amp and subtract them, physically I subtract them, so that this ES of t square goes away, PR goes away, as well as this PLO goes away, but this is real part minus of minus real part. So, this becomes double. There is already a half sitting there, so that half will cancel, but essentially the point here is that we have eliminated DC signals. Okay. So, I do not have to retain the DC signals for my in phase and quadrature components. Okay. So, I will directly be able to obtain the in phase as well as quadrature components without having to deal with the DC problem. One final point, we have obtained in phase as well as quadrature components. This is called as IQ demodulator or IQ receiver, because we are subtracting two photocurrents in order to eliminate the DC. This is called as balanced photo detection. Okay. Balancing means you remove the DC components from the two signals by physically subtracting the photocurrent. So, once you do that, the resulting signal will have no DC component at all. Okay. One final point is that incoming signals, we know that they are going to be polarized, although we have not talked about polarization. Optical signals can be polarized. Okay. So, it is possible in fact to have the two orthogonal polarizations, call them as X and Y polarizations, and to separately modulate the X polarization and modulate the Y polarization. Okay. So, if I have two polarizations coming in, I do not want to lose the information in both the polarizations. Okay. I want to extract information about polarization as well. How do I do that? Well, there is a simple, in a relative sense, there is a nice receiver called as polarization diversity receiver. Okay. This polarization diversity receiver simply takes the incoming signal ES of t, splits into two parts. Okay. This would be the X part of the ES of t and this would be the Y part. That is to say, we assume that the incoming signal is polarized, and I am representing the polarized signal by drawing a bar over the signal, right. I can put what is called as a polarization beam splitter to split the incoming signal into its orthogonal components. So, I can split them into X and Y. I can also do the same splitting by at the local oscillator as well. So, I will have ELO of t, which is also polarized. I can use a polarization beam splitter, split the X and Y polarizations. Okay. So, this would be the X polarization, this would be the Y polarization. I can use now the balanced photo detector in order to extract in phase as well as quadrature components here. Let us call this as IX and QX. Similarly, I will have a balanced photo detector here to extract IY, to extract the Y components of the photocurrents, right. So, I have IY and QY. Okay. Each of this, remember, needs a local oscillator which is being supplied by this particular component. So, take the local oscillator, split into two parts and then do a balanced photo detector to recover IX, QX, IY and QY. So, let us stop and continue in the next module. Thank you.